Hi everybody, this is Mr. Zarzak, and in this video I'm going to talk about the force and energy involved with springs. All right. So to start, we're going to jump over to this lovely application from Colorado FET. I have two identical springs suspended from the ceiling. All right, and so I'm going to start by taking this little 50-gram mass, putting it on the spring. Okay, we'll let it bounce around. Eventually it would come to rest. Okay, so when it comes to rest, it's at equilibrium. There's no net force acting on it. All right, if I look at the forces that are acting on it, though, okay, I do have two individual forces. I've got a little tiny little downward red arrow. That's the gravity, the force of gravity, or the weight of the 50 grams, which would be approximately, that. What would that be? That'd be 0.05 kilograms, so zero point 0.5 newtons. So I have half a newton down. All right, to keep that suspended, I need half a newton up. All right, where is that upward force coming from? It's coming from the spring. The spring is supporting the mass. All right, the spring force is a type of tension. We just call it the spring force because it's coming from a spring, okay? So then if I take and I put a 100-gram mass, all right, so twice as much weight now. All right, we put it on an identical spring. We let it come to rest. Okay, again, we see that the forces are balanced. All right, I have a larger downward force of gravity because, well, it weighs more. The 100-gram mass has a force of gravity or weight of, let's see, what would that be? 0.1 kilograms times roughly 10. So about 1 newton of downward weight must be balanced by about 1 newton of upward pull from the spring. Okay, so the spring force is now larger in order to support the weight. And the effect of this is kind of the important part, is look, the spring has been stretched a little bit farther in order to do that. Okay, I wonder if the trend continues. All right, so take the little 50-gram off. Okay, replace it by the 250. Watch it bounce. Oh, it's so much fun. Okay, and look. All right, the spring is stretched even farther in order to balance out the weight, to keep it in equilibrium. Okay, this 250 grams, so what is that, 0.25 kilograms, so roughly 2.5 newtons of downward weight must be balanced by 2.5 newtons-ish of upward pull from the spring, okay? And the result of that is the spring gets stretched farther. I wonder what that would look like on a graph. Let's go look. Okay, so if I were to plot this out, it would look something like this. All right, it would follow this linear trend. Okay, now this graph shows like the spring force on the y-axis. Okay, so put a little S in there for a spring force. Okay, and then the X is just how far it's the distance in one direction, okay, that we are stretching out the spring. All right. So you just think of each of these as like a data point. Okay, so I've got a couple of examples over here just to give us a visual. All right, that goes with this. And why are the masses different colors? I don't know, but that's okay. We can stick with this trend here. All right, so if I draw my little free body diagram for the green mass, okay, it's got a downward pull that we call the force of gravity. Okay, in order to be in equilibrium, it's got to be balanced by an upward pull. All right, that pull comes from the tension in the spring. Okay, so the arrows would be the same size and just point opposite directions. Okay, if we look at the little brass mass over here, okay, well then to be in equilibrium, look, it's a different color, so we can change the color too, because that's important. All right, so this would weigh a little bit more, okay, which means that we need, let me move that out of the way, we need a little bit more spring force to balance it out. Okay, with this red mass, same idea. Okay, this one weighs a little bit more. Whoa, a lot more. So we need a little bit more force to balance it out. Where's that force going to come from? It's got to come from the spring. Okay, so these would just be our free body diagrams for these three scenarios. I don't have to line them up, it's just for comparison's sake. So just so you can see, all right, as it weighs more, the force requires grows, okay? And what's interesting and useful about it is it follows this linear trend on the graph. Okay, when we're looking at graphs in physics, okay, we can read the graphs, but we're always looking to see if we can get something more out of it. In this case, we can. One of the tricks we do is we look at the equation of the line. All right, so the general form of the equation of the line is just y equals mx plus b. All right, but then we take and we manipulate the equation. We basically rewrite it with the actual variables that are on the graph. Okay, so the first thing that kind of jumps out is the y-intercept. Okay, if I look at the graph, okay, we see that the graph hits at the origin. Now this is for what we call an ideal spring. All right, but experimentally, we would need to write our equation and plug a point in to determine that B, but this is just conceptual. Okay, so no y-intercept. So we get this simple relationship y equals mx. If we look at what's on the vertical axis, what is our y variable? It's the spring force. Okay, so we replace that y with the spring force. The m is the slope. All right, now I don't know what the slope of this graph is. We'd actually have to have actual data, but I can see that it's linear, all right, which means that it's a constant slope. So this is just like some number, right? The variable on the x-axis is, well, x. Okay, so it's the amount that we are stretching. This would work for compressing too, by the way. We're working within one dimension. Okay, so one single dimension, so we just call it x. Now, the fact that this slope is linear, okay, really corresponds to any what we call a Hooke's law spring. All right, the size of the slope is really a property of the spring itself. If I had a stiffer spring, one that was like harder to stretch or compress, okay, I would still get a linear relationship, but the slope would be steeper. Okay, the graph would be a lot steeper. All right, if the spring was easier to stretch or compress, okay, well then I would still have linear, but the slope wouldn't be as steep. Okay, it would be something more kind of like that. Okay, but just linear, not like that sloppy line that I just drew. All right, so because the slope is constant, all right, that's actually a property of the spring. It's a measure of how stretchy or stiff the spring is. So we're very very creative in the way that we name things in physics. So we call this the spring constant. How creative is that? And we give it a letter K. All right, it's a number of newtons or force that's required to stretch it some distance in meters. All right, this is the equation, all right, that describes the relationship between force and stretch of a spring. All right, now this is commonly known as Hooke's law. All right, when you read about Hooke's law, very often you will see Hooke's law written like this: F equals negative kx. Okay, the reason that when they are describing this mathematically, that they'll put that negative in front of the kx is because the spring force is a resistive force. See, so like in each of these cases, the gravity, the weight is pulling the mass down, so the spring resists that pull that's on it by pulling back up. Likewise, if we were to take a spring and try to compress it, okay, we would try to push the spring inwards and it would respond by pushing outwards, always in the opposite direction of any force that's applied to it. All right, so that's the idea behind this negative when you read about Hooke's law, is it's there just to indicate a resistive force. When we work with Hooke's law, okay, though, I don't want you to get fixated on that negative. No, 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 no. Okay, Hooke's law is kx, and then the direction of the force, positive or negative, is going to come from your free body diagram. All right, when we're writing equations with spring forces, all right, there's going to be multiple forces involved. All right, you set a positive direction. If the spring force points in the positive direction, it's positive. If it points in the negative direction, it's negative. Okay, so like I said, don't get fixated on that negative part. It's just an indicator that it is a resistive force. F is equal to kx for a spring. All right, the second trick that we do when we're working with variables on a graph is we look at the slope and then we look at the area underneath. Now, we don't always get something from the slope. We don't always get something from the area. All right, but in this case, we get something from the slope and the area. Okay, the area underneath is a triangle. We know how to work with a triangle, but really, if we think about this just for a second, it's force and then the displacement of the spring. Force times displacement, that's work. Okay, so we're going to use that here. But first, let's just look at the actual area underneath. So area is equal to 1/2 base times height. Okay, and then if we replace the base and the height with what's actually on the graph, 1/2, all right, the base is just how far we, in this case, stretch the spring. All right, and the height of the spring is the spring force. Okay, well, the spring force, that's just this kx. All right, so I'm going to do a little mathematical substitution here. Fancy. Okay, where I replace spring force with this. Let's do it in red. Let's make it really fancy. Kx. All right, the force that acts on the spring. All right, and if I take and I carry all this through, I get this area is equal to 1/2. All right, I'll bring the k out in front. X times x, which is x squared. All right, that relationship is important for our spring because, all right, really we're taking the force and we're multiplying it by how far the spring is displaced. Okay, well, that's just the definition of work. Well, it's not the definition of work. I misspoke there. It's force times displacement is the way we can calculate All right, the work done on a spring. Work, the real definition, is the change in energy. Okay, that's the bigger concept. And when we take and we either, in this case, stretch or compress a spring, here we're stretching, okay, we are going to give the spring potential energy, specifically spring potential energy. All right, so we put a little S there to indicate spring potential energy. By doing work on it, to stretch it, we give it spring potential energy. All right, if we take and we expand this out, the little delta, all right, so we got final, a little F there, minus spring initial. All right, if you look at a graph again, okay, if the spring is not displaced at all right, in other words, if you don't stretch it out, if we haven't applied any force to it, well, then there is no spring potential energy, no F, no D, no work, no change in energy. All right, and so that just cancels out, and we're left with the work that's done to stretch or compress a spring tells us how much spring potential energy we have. All right, so we're just going to take and sub this in now, so we get this spring potential energy is equal to 1/2 kx squared. All right, this is the equation that describes the spring potential energy stored in a spring when you stretch or compress it. And then this is the equation that we call Hooke's law, all right, that describes how much force is required to stretch a known spring some distance or compress it. All right, this spring potential energy is sometimes called elastic potential energy, okay, which is just a more generic term for stretchy or compressy energy. All right, we use the terms spring potential and elastic interchangeably for our purposes, at least for the time being. Okay. All right. Well, anyways, so this is Mr. Zarek saying thanks for watching. All right, and we'll see you next time.